So I am going to serve as the moderator for the final session. As Kent has emphasized, CFAR has key strategic partnerships. And in this last section, we'd really like to invite some of our partners to join us. I'm also especially pleased to do this because I have a personal connection to each of the speakers that I'll share with you as we go through. James Moody is the Robert Cohan Professor of Sociology. He's the founding director of the Duke Network Analysis Center, and he's also my neighbor on Pinecrest Road. So I'm especially pleased to see him here in the workplace. Jim, thank you so much for coming and speaking with us.
All right, thanks for having me here, and thanks for everyone for sticking around to the last session. You've probably been here since the wee hours of the morning, so I'll try to keep this as light and quick as quickly as possible. I would like to start with a great social scientist, Peter Blau, who wrote in 1964 that to speak of social life is to speak of the association between people. They're associating in work and in play, in love and in war, to trade or to worship, to help or to hinder. It is in the social relations men established that their interests find expression and their desires become realized. Right, this is what you might call the strong program in social analysis, right? It says that what it means to be a human being, what it means to be a person, is to be connected to other people. And when Peter was in a joking mood, he said you could tell this because the difference between a glutton and a gourmand was company, right? And what network analysis, or social network analysis in particular, is interested in doing is capturing this social feature, making sense of what it means to be connected to other people and how those connections might matter. And this is an old field. It started with Jacob Moreno in the 1930s, and he had this grand vision that said if we could ever get to the point of charting a whole city or a whole nation, we would have a picture of a vast solar system that influences conduct the way that gravitation does in space. Right? That's the promise of social network analysis, that if we could just identify and map and make sense of these connections between people that we know matter, we could actually do something like social physics and make a sense of the world in that kind of rigor and that kind of wonderful specificity. It turns out, of course, that it's been a lot harder to do that, but it's something that's drawn a lot of interest. And this is just a quick citation count, number of papers count from all papers on the Web of Science that lists the word networks in the title. Right? And so about 4% of all the papers that include the word health in the Web of Science also include the word networks. Now, 4% might not seem that big until you realize that it's just about the same size as the number that reach obesity. Right? So this is an area that people are becoming increasingly more interested in, and they're trying to understand. And what we're doing in the Duke Network Analysis Center is trying to help provide resources to make sense of how these things work. So I have two goals today. I have a DNAC hat, which is the Network Analysis Center. I want to introduce you a little bit more about what network analysis might be and the ways it might be useful to CFAR participants. In particular, I'm going to give what I consider the two fundamental social network mechanisms, the reasons why we think that networks matter. And so I'm going to speak in a little bit of my own favorite sort of piece there. And then I have a second hat, which is a network epi hat, which is the bulk of my own work. And I want to talk about the ways in which short-term or cross-sectional number of partners, the number of sexual partners people have, can create the substrate for an epidemic that could remain endemic and spread widely, or one that would fail. And if there's time, and I assume John will flag me down if there's not, I have a second piece that talks about the timing relations, but that's sort of, we can take it or leave it. Let's start with the connectionist view. All right, so from the connectionist position in social network modeling really focuses on the links between particular actors. And you can imagine the best way to think of this is to think of its opposite. So if you think of an isolationist view, you might have a sample of kids here in red, and I've gone out and interviewed them, asked them about their last two sexual network partners, and I could ask you all kinds of things about their relationships. Have they used condoms? Like how their frequency of interaction, what kinds of interactions they have, and so forth. But if I really want to understand the likelihood of getting a disease, I really want to know how they're embedded in the underlying sexual network that characterizes their population. These are real data on adolescents from a school in the Midwest. Each point is a kid, and each tie is a sexual relation between them. And some of these nodes, you can see, right, that look exactly the same at the individual level, are disconnected from the rest of the population and essentially not at risk. Or others are, again, have only two partners locally, but are connected to 300 other people in this population who could be at risk. This is the graph I always show high school kids, right, to get my ooh response. It's pretty effective. The connectionist model of social network models is really, if you want to, the key way to think about it is that these are networks as pipes. And what we're interested in is how things move through those pipes. And the connections to CFAR, I think, are pretty clear. This is how disease moves through a social network population. This is how gene regulatory ideas move from one protein to another. And so you can think about the connectionist model is where a huge amount of work in network and system science has gone in the last 20 years. The positional model asks how your pattern of relations shapes the constraints that you have in a social system. And take a system that looks like this. We have 5 randomly chosen nodes, 2 of whom share romantic love. Those 2 feed 3 people who fight with each other. Right? Now, if you think about this for just a minute, of course, we have labels for these kinds of positions. And what we think about instead in this line of work is that we want to move not from the world where we already know the labels and induce the relations, but the opposite, right? We've given a set of relations. They could be exchange relations. They could be who you buy your drugs from, who you go to for advice, all the rest of this. And from that, we want to generate the endemic rules that guide this social system. And the reasons that this might be interesting for people in the CFAR sort of world is if you want to think about how people make use of their drugs, right, how they make use of their treatments, how they provide their position in the community, you really want to know what the rules are that guide the social system they're embedded in. And social network analysis, and particularly these kinds of structural features, can be useful in helping make sense of those pieces, even when the informants themselves are not necessarily sure what's going on. So this leads us, of course, to what all sociologists do, which is we create 2-by-2 tables, and that's basically the world of our theory. And there's a whole array of things that you can think about in terms of how you might want to play with these kinds of elements as either cause or effect. What I'm going to talk about today is really just one piece of a small part of this, which is diffusion modeling, so networks as a cause in the pipes sort of realm. If you're interested in more of this, right, if you want to have this little teaser has been at all interesting, we have a very active group at the Network Analysis Center. I just discovered this morning that our webpage is horribly out of date, so I had to chew someone out about that. But otherwise, our mailing list is relatively up to date, so please join on. It's a relatively low volume set. We have weekly seminars, and it ranges from biologists to sociologists to people from the military. It's a very wide-ranging group of people speaking, and you can learn a lot about these methods and the way that these things work. All right, now on to the substantive question of the day. What network features contribute most to diffusion? It turns out that if you think about this problem carefully, there are 2 basic types of elements. One is the topology, or the shape of the network, and one is the timing. I probably won't have time today to talk about the timing, but if we do, I'll go on to that. Within the topology of the network, what we really care about is this notion of connectivity. Is it possible for one person to reach someone else? And if so, sort of what's the nature of that connectivity? Is it a short path that I can get to you quickly, or is it a redundant path that's robust to lots of interventions? Why might this matter? Well, imagine that I have a simple probabilistic transmission across the network. If the number of steps, the number of handshakes from me to somebody else is very long, then the probability that bit gets transmitted across the network is an exponential function of that probability, right? So it's the probability that transfers over 1 step and 2 steps and 3 steps and 4 steps. But if I have multiple paths, right, then I get routes around. So if you have a simple probabilistic process on a network with multiple paths, you get reinforcement. And redundancy creates an or condition, essentially, in a world that would otherwise be an and condition. And so this is why we care very much about the robustness of the tie, not just the length of the tie. And why might this matter? From a very simple example, these are data from Colorado Springs collected in the mid-90s on 2 types of relations on a population that was thought to be high risk to HIV at the time. One, commercial sex workers and their Johns, which is the network you see. There's a commercial sex network on the left. On your left, yes. And the other is a drug sharing network. And what you see in this is, I think, a fundamental feature about these kinds of systems. The characteristic structure of a sexual network is string-like. You have these long dendritic ties that are relatively fragile and easy to break. Whereas a drug sharing network, a needle exchange network, you share needles in groups, and it creates these very dense cliffs with lots of different paths around. So part of the reason that it's so much easier to get HIV epidemics sustained in a drug sharing culture is not just that, of course, that the probability of transmission is so much higher when you're breaking the blood barrier, but also that the social structure is one that carries the disease and is redundant to interaction or to interruption much more than the sexual network side is. And also another thing to point out here that people often, oops, I don't know what I did there. There we go. There we are. Is that the notion of redundancy is built into the global structure of the network, not just the local structure. So a lot of your commercial sex workers in this relatively small town in Colorado are on the edges of the network. And there are some, particularly their pimps, that have low numbers of ties internally, but are nonetheless multiply reconnected. This is what's known as a 3-core in the network. So there are 3 completely unique paths connecting every node in that yellow set, right? And so notions that your simple individual level features, like your number of sexual partners, are determinative of your position in the network are too simplistic. You really need to make sense of what this underlying or this overarching global structure looks like. All right, so that was what I just said. So we're going to try another. I got ahead of myself. A lot of the energy that's gone into sort of understanding the sexual network sort of platform for HIV transmission has focused on people with lots of high degrees, with lots of partners. But in the short periods of time in which HIV is most effective, that is the windows of time that are relevant for disease transmission, the average number of sexual partners people have over their lifetime is pretty irrelevant. What you want to know is the number of partners they've had in the last year, say. And that distribution tends to be what we call low degree. There might be a few high stars out in the network, but most of the population has like 1 or 2 or at most 3 partners. And so we want to know what happens when you look at those low degree networks, what's the likelihood of observing a connectivity structure that could carry disease. And this is actually a nice object lesson in the way that network systems work. So if we start with a relatively simple low-degree population, here the average is 1.68. So on average, every partner has, most people have 1 partner, a few people have 2 partners. In this kind of system, you get very dendritic structures that are really fragile. There is no reconnection at all, and the largest connected component in the largest set that could be connected is less than about, let's see, out of a network of 10,000, we're talking at 215, right? So it's a really small proportion of the population. Shift the distribution just a little bit, you start to get what graph theorists call a giant component, which is that there's a single, I keep hitting the wrong button, a single set in the network that is connected, a lot of little pieces, and but a growing group that comprises the connectivity structure of the network, increases it a little bit more and a little bit more. If you move a corpus of this just a tiny little bit, right, from 1.68 to 1.87, you move from this world that's completely disconnected to a world that is deeply reconnected, right, with very small changes at the local level. To put this in context, the average number of degrees, or the average number of partners, could be thought of as moving along a very small range in the sort of total volume of this space. But the shift from the size of the people who could ultimately be reached, the size of the largest component, which is the dark blue line, or the size of the people who could be reconnected through multiple independent paths, right, is a very sharp transition point. And this is something that happens commonly in these kinds of systems. You have what's known as a phase transition. You move from a world where there's nothing going on, almost nobody is connected, to a rapid shift to where almost everyone is connected. Now, if you shift your idea a little bit and think, well, let's not focus on just the average number of sexual partners, but the shape of this distribution, there's been a lot of talk in the literature about what are called scale-free networks, networks where you have an extremely long tail. Most people have 1 or 2 partners, but there are a few NBA basketball stars out there who have hundreds of partners, and what we want to know is what does this transition look like for them. In this case, you also see a world where you have a sharp transition, but it's not nearly as sharp. It's a much more gentle transition as you move through the volume space, and the proportion of people who are reconnected are smaller. So in the types of settings where you have these low-degree worlds, we actually see a sharper transition, where it's really probably harder to know which side of this transition you're on, and you have less of a chance to respond to a quick and sort of a rapid cascade of connectivity. Well, with colleagues at Colorado and University of Washington, we were interested in what the entire field of these kinds of networks look like and these network spaces. And so we imagine a problem space defined by the volume of the tie and the variability, the spread across the tail. And if you imagine this space as a universe of all possible networks that could exist in this area, the 2 distributions I just told you fill 2 lines in that space. But of course, there's an entire area in this space we want to explore and ask what are the network connectivity implications in these different regimes. And so what we did is something pretty naive in some sense. We just literally bootstrapped every viable degree distribution in that space. And so there's about 98,000 of them. It's viable because you have integers, right? So it's not actually an infinite space. And so we just generated every one and simulated a bunch of networks for every one. So it's completely boneheaded, but it's effective. It works. And these are some samples of what these distributions might look like. All kinds of different shapes, but they fit into this space quite nicely. And then if you look at the kinds of components that generate across them, you get something that looks like this, right? Again, red are your reconnected sets. Blue are your dendritic, sort of weakly connected sets. And the space has a really interesting structure. I'm going to put in the upper sort of corner where you have long tails, you get these really star-like structures. And these star-like structures have a very long blue sections, very long single connections, but a pretty dense core. If you shift up the volume level but down the variability level a little bit, you get very similar structures, right? So you get the same exact kind of structure, or very similar structures, with very different distributions, depending on the balance or the trade-off between the number of partners a person has and the distribution of that partners across the population. And of course, you can walk through all of this space if you want. As you increase volume, the cores get deeper. If you increase both volume and decrease variability, you get these really, really dense sections where a disease would take off quite quickly and move rapidly through the setting, or at least there's nothing in the structure that would cause it to slow down. So if you imagine mapping then this entire space, what do you see? Well, you see that the contour lines here are really the thing to focus on. These, and they don't come up very well on my screen, but you can see that there are contours here that are leaning to the left in this side and to the right in this side. And what it tells us is there's a couple different regimes. On the graph on the left, what you have are the size of the largest component. On the right, you have the size of this giant bicomponent, or this reconnected core. And what you find is that in the largest bicomponent, if you actually, if you were to chop off the tail of the distribution, if you were to keep the distribution, the average volume the same, but chop off the tail, you actually increase the size of the number of people at risk in this giant connected bicomponent. Now, why is this of interest? Right? If you think about what typical police enforcement is in these kinds of settings, what you do is you try to arrest commercial sex workers or discourage commercial sex workers from engaging in their practice, which is effectively chopping off the tail of the distribution. If you haven't simultaneously changed the demand for sex, right, if you haven't changed the volume on the set, then you've essentially moved from the top of this arrow down to the bottom of this arrow, and you've made your problem worse. What you want to do instead is push the demand for sex, the volume of this piece to the right, to the left, excuse me, so you're down in this region instead. Now notice if you're in a population setting where you're over here, right, then it's a little bit different. Here it's the case where the long tail is higher than the short tail. But if you cross this regime about 1.8 average number of partners, you actually get worse when you trim off the tail. We take this as a lesson, and the lesson we take from this is that network structures are relatively complex, and they have implications for the kinds of outcomes you might find that aren't obvious at the node level. Right? Actions that make sense in one regime don't make sense in another and can actually have pretty negative consequences. And so we're continuing this work now to ask how this engages in the dynamics of the network, but right now this is where we're at that. How much time do we have?
13 minutes.
Oh, all right, then we'll go on to the second problem. My joke with my students is that I talk fast, but they learn how to listen fast. So everything that I just showed you was done on what we call a static network. So all the edges exist at the same time, and that's all there is to it. There's a debate in the literature about the timing of relations, and it turns on a notion of concurrency. And concurrency is a problem, or is a feature of a network when people have partners at the same time. So I start a new relationship before I finish the old relationship. That's concurrency. And Martina Morris and her colleagues in particular have argued for years that this is a significant increased risk at the population level for the spread of HIV. Others, including Saunders and Stillwagon, argue pretty vociferously that it's not, that there's no association between the two. And so what I've tried to do as a graph theorist is figure out what are the actual mechanisms under which the timing of relations could create or not the spread of a disease. And that turns into a pretty simple problem. If you imagine the contact network we observe, what we're really interested in is a subset of that network that can be decomposed in three parts, right? The first is the observed contact network, who has sex with who. The second is the exposure network. That is, who is it downstream in time from somebody else. And the third would be the transmission network, which is a stochastic function on top of that temporal network. So there's a random transmission probability, which is the tree overlaid on the second one. If you think about what this looks like, the ordering in time is crucial, right? So these edges are labeled by when they occurred. So the relationship between A and B starts at time 2. The relationship between A and E starts at time 4. In this case, I just treat them as discrete times. So it starts and ends at time 2, for example. And if you follow the simple rule that I can only pass a pathogen forward in time, then A can't reach everyone in this network. Right? There's a limited number of people that A can reach. And that's because once A has a relationship with D at time 3, the relationship between D and E is already over before the relationship between A and D started, and so any infection introduced by A can't spread any further down that path. Now, the transmission network then is just some random sort of function on top of this limited subset of edges in the exposure network. So if we can track the shape of the exposure network as a function of concurrency, that'll tell us a lot about the underlying substrate on which disease could transmit. So how do we make sense of this in the world? Well, we think about it as concurrency we define as the proportion of edges that overlap in time. So this is a concurrent edge. This is a non-concurrent edge or a serial edge. And the beauty about concurrent edges is that they have an effect on the reachability, this temporal ordering, who's downstream of me, that reaches much beyond the focal node of the individual. So consider a simple example here where all edges occur at the same time. In this case, we'd say that everyone in the network is reachable to everyone else. It's a completely dense setting. On the other hand, if we now introduce a little bit of timing, right, so the edges on the left occurred at time 1, the edges on the right occur at time 2, we see that everyone on the left could possibly infect everyone on the right up over here, but most of the people here can't get infected by the people on this side. You cut it in half. Now, if I then take this exact same network and change the timing of a single tie, I just changed the DG tie to start at time 3 instead of time 2, I've cut the exposure risk in half. And what's important about this is a population level feature because the vast majority, only 2 actors in this network change their behavior. So if you're out looking for a correlation between an individual's concurrency, right, and their infection risk, you're not going to find it because the infection risk isn't my own because I have concurrent relations. It's what I've done to the population downstream of me and how that changes the rest of the population. The reason this occurs is because of the ordering of relations. When relations are sequential and don't overlap in time, you can only move forward. And so you get this tree structure where each edge can only pass on to the next adjacent edge. Right? When you add an overlap in time, so the edges are concurrent, they can now go both directions. You go from what used to be a single switching station to a symmetric relation. And so you move from an asymmetric temporal ordering to a symmetric temporal ordering, which can potentially double or quadruple the number of downstream paths from every edge that you originally had. And that's the mechanistic feature of how a graph, how concurrency could increase the exposure risk. All right. Now, that's a mathematical necessity. That has to be true. But we want to know how big the effect is and why and how it interacts with this thing that we can measure directly, which is the contact structure. So we generated another simple simulation, which is we took a bunch of observed networks, and each of those networks, we assigned them every edge of the network a duration and a start time that we varied in such a way as to manipulate the concurrency level. And the beauty of this is it allows us to hold constant all of the network structure features, all those connectivity features, and all the duration features, but manipulate the concurrency structure. And so we can ask, how does concurrency by itself affect this overall exposure risk, conditional on the shape of the network. So we can interact with something like the number of paths that are available to be moved through. And so the measure we use at the structural level is something we call structural cohesion, which is the number of paths that are the independent paths between every pair of nodes in the network. And so we just take the average across everyone in the set, and there's a couple examples there. And these are what these networks look like. They're small little networks. They range in size of the average is about 150. They range in size from 70 to 300. And they have features that we think are representative of the kinds of networks we care about, which is they tend to have low degree, right? Most people have a small number of partners, but there are a few stars that have lots of partners, and there are subsettings that are really dense. And so we have a lot of observed variability in the structural cohesion. Any guess of what kind of networks these really are? Because they're not sex networks. These are scientific co-authorship networks. That there's a correspondence there is just a nice coincidence. So we run the simulation across there are a proportion of edges that we allow to be concurrent, the proportion reachable, and this is the result for those 4 networks that I just showed you. And the pattern is pretty striking. In networks that have really highly cohesive structures, that is, where there are lots of redundant paths already built into the network, the proportion reachable is already very high, and so the effective concurrency, while positive, is shallow. Right? So there's not a lot of room for concurrency to have a huge effect. Whereas the networks that are the least voluminous, so the networks that have the most dendritic structure, right, those are the places where concurrency, the timing of edges, have room to make the most effect and can have an extremely strong differential in terms of the overall reachability that's effective in timing. You can move from remember, these are the exact same network structures. Just by changing the timing on the edges, we can go from 20% of the population exposed to 100% of the population exposed. And this is without changing the edge order at all. This is just the timing on the relations. Extend that across all of our simulation. We have, in this case, again, about 50,000 unique iterations or simulation settings. And the results are very much the same. In really low cohesion settings, you have a very strong positive effect. As you move up here, where average connectivity is really high, the effect is still positive, but not nearly as strong. You can model this using a logit link because it's a limited top on the set. You can't go above 1% of the population or 100% of the population. And this is the kind of fit you find, right? And so it's a really nice sort of clear story that in populations where the number of partners is small and the structure is fragile, concurrency is a crucial determinant of the overall spread of exposure, or the overall exposure risk. Whereas in settings where the underlying context structure is highly redundant, there's not much room for concurrency to have an effect. So we think this is a nice finding because what it tells us is that if you're out there looking at different countries and finding a different correlation, and you're finding no correlation with concurrency, because there's a necessary relation mathematically between the ordering of ties and exposure, it must be something like this structure that is confounding the relation, that makes it hidden. And so what you need to do is not stop asking about concurrency, but figuring out what it is that is covering up the concurrency effect that has to be there. I'm almost done. If you want to think about what network really matters for CFAR research, it's probably this one. Right? This is just a fun joke. It's my last slide. It's the political polarization network, who votes for who in the American Senate. And in the period of NIH doubling, right, you'll notice that in that part of the world, we were living in a world where people, Republicans and Democrats, actually voted together from time to time. There's always cores who don't. But now we don't. And so if you want to think about the network you might really want to manipulate, it's probably this one. Thanks, guys.
Questions? Melissa?
Yeah, this is great. Can you talk a little bit about just the challenges and potential joys of measuring sexual networks in particular? And I mean, to be able to kind of come up with this seems really complicated, but from a data collection perspective, what does that look like?
Yeah, there are two answers to that. So if you want to get the global network, like the high school network I showed you, the challenges there are fundamentally privacy and trust. And so what you need to do is to identify ways to convince IRB and parents, if they're juniors, that you're going to be able to keep this data truly private. And in this case, we were able to do it with an audio CASI self-administered design that really made it, it was a face-to-face interview, but for that portion of the interview, the student put on headphones, they were using the laptop, and it was very private. There was still, we had to build some remarkable firewalls between the actual names of the students and what the investigators could see, so that linkage is kept in Canada, for example, so it's not subject to subpoena and things like this. So there are some crazy things you have to do to make sure that happens. I think that we have very few of those studies because they're very hard to do for just that reason. There's a great study that's been done in India, and I'm going to forget the gentleman's name, that spoke at DNAC last year, using cell phones, where they were actually able to take, for men who had sex with men, take the RID chips out of their cell phones and get the list of all the people they've called in the last, for as big as the memory would go through, present that as a roster to the respondent, and say which of these other people are MSM, right? And so there are things you can do that are remarkably creative, right? But the challenges are fundamentally privacy and security, and so you have to work out how those details work. And this is why I think the other data set that I use the most often is the Colorado Springs data. And this was collected by John Potterat and his colleagues, who are the public health workers in Colorado Springs at the time. And they had spent 20 years with this population building trust. And so the commercial sex workers, the drug dealers, everyone else that was sort of the active population in that set, deeply trusted John and his colleagues. He knew them all by name, and he had worked with them, and he felt that he had done the gumshoe work necessary to get them to confide in him and tell them who they were connected to. And he also knew enough about the setting to make sense of it. Now, the problem is that we want fast response in a lot of places, and we don't always have the luxury of tapping into that kind of piece. And so there are two nice solutions to that. One is that our simulation tools have gotten remarkably good. And the beauty of these simulation tools is that I can ask you questions, or I can ask anyone in the population questions about their patterns of relations without having to actually identify the alters. And then I can take that information and build a simulation model that is accurate enough to get us at the types of features, connectivity, timing, and redundancy in particular, to get a relatively nice image of what we think the network probably looks like. Now, there are some obvious bounds on that, but that allows you to essentially lower the boundary of the trust part of that network. You're not asking people for actual names. You're asking them for the last central partner, the partner before that, the partner before that, and they can give you the timing on that. Giovanna Merli and I have a paper that's about to come out at Demography where we did this using data on commercial sex workers and linked that with data from the general population in China to look at the structure of that network. And it's remarkable because you can use a setting like Shanghai where you could never do a general population survey, but through the simulation tools you can generate a really nice, pretty accurate, we think, image of what the underlying network looks like. What's missing there is the obvious point is you'd like to be able to walk between them. And we've corrected these simulation models for the data we have, but there are remarkably few of these global networks that we have to test them against. So we think they work, but our bounds of ignorance are pretty high there. So does that answer the question?
Jim, thank you for a super talk.